So now we discuss uh, about flywheel of a punching press. So in a punching press, actually the energy is supplied by a motor, and there is a slider crank mechanism, and this is the punch, and this is the plate. The plate moves and gets punched. So this is a punching machine, and here uh, 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 the requirement of energy is intermittent, because high energy is required during punching, but then so for the punching the crank moves from theta 1 to theta 2, but after that high energy is not required, or high torque rather, high torque is not required. Large torque is required during punching to shear off this portion, but when there is no punching, then the torque requirement is low. So the torque here, the torque requirement is intermittent, but the supply of torque is from a motor, so we assume that the motor applies a more or less constant torque. So from theta 1 to theta 2 the punching takes place. So let Et be the energy required for punching one hole. For a stable operation, the energy supplied to the crank for one revolution should be equal to Et, because if Et is the energy required to punch a hole, then in a cycle, because there will be one punch in a cycle, so the total energy supplied by the motor must be equal to Et, and Et is the energy required to punch a single hole. And since this hole is being punched in a cycle, the total energy supplied by the motor in this cycle should be Et, a little more than Et maybe, to overcome the frictions and everything, but okay, more or less it is Et. So the fluctuation, so here you see, so this is the torque available from the motor, and the required torque is 0 up to theta 1, then suddenly it increases. We have approximated it by a rectangle, then again it decreases and becomes 0. So this total blue portion has to be supplied in a cycle, has to be supplied in a cycle. So energy supplied during punching, so, and what is the fluctuation of energy then? This above this line, this rectangle is actually the fluctuation of energy, because what happens, the motor energy gets accumulated, and here there is a large requirement, so it gets this portion, but the loss is much more. So the loss is energy spent due to punching is this blue portion, and the energy supplied during this portion is this. So loss, so gain, huge loss, and after huge loss small gain, then after this again gain. So in this way it goes. So here the energy is maximum, and here the energy is minimum, and the fluctuation of energy is the portion above this. So the fluctuation of energy is actually this much. So this is the fluctuation of energy, and that means, and what is this, so energy supplied during this whole thing is Et. So Et by 2 pi into theta 2 minus theta 1 is this blue portion. So if we subtract, and if this is Et, this whole energy is spent during punching, so this is also Et, and the fluctuation is Et minus this portion. So the shaded portion is the fluctuation, and that is this. Now we assume that this theta 2 minus theta 1 portion is small, and 2 pi means the crank rotates by a complete revolution, and during the crank, while the crank rotates a complete revolution, the piston goes from one end and again comes back there, so it is twice the stroke. So this 2 pi corresponds to twice the stroke. So if we assume, if we can approximate this theta 2 minus theta 1 by the ratio of theta 2 minus theta 1 by 2 pi by t by 2s, because 2 pi corresponds to 2s and theta 2 minus theta 1 corresponds to t, because theta 2 minus theta 1, it goes from here to here, it is t, and for 2 pi it is twice the stroke. So twice the stroke means for the crank radius. Twice the stroke means for the crank radius. So Et into 1 minus T4 is approximately equal to I Ks omega square. So this is actually the starting point for solving problems. So a punching machine punches 3 holes per minute. The diameter of each hole is 4 centimeter and the thickness of plate is 3 millimeter. The stroke of the punch is 10 centimeter. The work done per square centimeter of sheared area is 450 joule. The maximum speed of flywheel at its radius of gyration is 28 meter per second. Determine the mass of the flywheel so that its speed at the radius of gyration does not fall below 26 meter per second. Determine power of the motor required. So hint, cutting occurs between theta 2 and theta 1 and T by 4R is equal to theta 2 minus theta 1 by twice pi. So what is the fluctuation of energy? Fluctuation of energy is this, and this is half maximum speed minus minimum speed. So omega 1 is actually omega max. This is omega max square and this is omega mean square. So, and I means the mass of the flywheel into radius of gyration. So, and you can take this k inside, and that means if you multiply this k by the angular velocity, this is the maximum linear velocity. So this is the v max square, and this is v max square, and this is v min square. So now you just put the values, and Et is the area of shear, the cylindrical surface of a cylinder, the surface of a cylinder, this surface, this is pi into 4 pi d into t into 450, because this is in millimeter, this is in centimeter per square centimeter. So 4 and this 3 millimeter has been made centimeter into 450 into this, t is 0.03 3 millimeter by 4r. R is stroke of the punch, so r is 5 centimeter. Okay, stroke is twice radius, so 5 centimeter. Sorry, r is 4r, so r is stroke is twice r, so stroke is twice r, so r is 5 and 4r is 0.20, so 0.20 meters, 0.20 meters, 0.3 millimeter is 0.003 meters equal to half mf, and this is 28 square, this is 26 square, and from here you find out the mass of the flywheel. So we stop here and actually we here we come to an end of this course.